Infrared camera is a highly specialized technology to capture images and video in the infrared spectrum. This enables us to see and analyze objects and environments in a whole new way. It is available in different forms, from simple smartphone accessories to handheld version, to high-performance systems. In today's video, I will break down the fundamentals of this cool technology and provide a scientist's perspective on its future. The uniqueness of IR camera is its ability to transcend the limitation of human vision. Our vision is based on the light detection by rod and cone cells in the retina of the eye. These cells contain photopigments which only respond to a small portion of the electromagnetic spectrum between 350 to 700 nanometers. By detecting light outside this range at infrared wavelengths, the IR camera enhances our perception of the world. Before going into the details of how it works, let's first understand the origin of infrared radiation. All bodies emit thermal radiation because of their temperature. At the quantum level, the radiation comes from the thermally excited atoms and molecules within an object. Whenever a single excited atom inside a body decays to ground state, it emits a quantum of light, which is the photon. The wavelength of this thermally emitted photon depends on the temperature of the body. For example, at very low temperatures like those of the outer space, the excited atoms emit microwave radiation. At room temperature, atoms get excited to higher states and emit infrared radiation. And the same thing happens at the surface of the sun, except that the atoms get excited to very high states, causing thermal radiation at lower wavelengths near the visible spectrum. This is how the overall spectrum looks like for thermal radiation from the sun versus the thermal radiation from near room temperature bodies. The IR camera essentially captures the thermal radiation from bodies at infrared wavelengths, which is why it is often described as thermal IR camera. Different materials emit IR light differently, and it is that difference which shows up as characteristic features in the IR image. Let's understand how the IR camera works. At the system-level architecture, the infrared light coming from the world is focused onto a detector plane array, also called as focal plane array. Each pixel within this array is a carefully engineered micrometer-sized detector which converts incident IR signal into an electric signal measured by the integrated readout circuit. After analog to digital conversion of the readout signals, image processing algorithms are used to create the final RGB image. This image is then displayed on a screen which itself contains tiny LED light sources that emit visible light for us to see. All of this happens within a fraction of a second. Let's go deeper and understand infrared photodetection, which is the most crucial part of IR camera. There are two different detectors called as photon detectors and thermal detectors. The photon detectors directly convert the IR signal into a measurable electric signal. For thermal detectors, the IR signal heats up the detector pixel and the resulting temperature change is then converted to an electric signal. The photon detectors consist of semiconductor photodiodes. When infrared light hits the depletion region of the diode, it causes the electrons to transition from a lower energy state to a higher energy state, resulting in the creation of electron-hole pairs. These electrons then move towards the positive terminal of the cell, creating an electric current that can be measured by a readout circuit. It's important to note that only IR photons with higher energy than the band gap energy difference, or a shorter wavelength than the cutoff IR wavelength, can be detected. This means that we need to use low band gap semiconductors to measure the IR signal. However, these semiconductors can also produce an additional photocurrent called dark current due to thermal excitation of the electrons across the band gap at room temperature. To minimize this dark current and improve sensitivity, we need to cool the photodiode to very low temperatures. That's why most IR cameras that use photon detectors are cooled using microcoolers and are referred to as cooled IR cameras. The second approach of thermal detectors uses what are called as microbolometers. These detectors consist of something called phase change materials which are sensitive to small temperature changes. If this material is heated, its properties like electrical resistance can change. Microbolometer detector has thin film containing this phase change material, and it is suspended using tiny little insulating microposts. When the IR light hits the suspended pixel, it heats up the phase change material, causing a change in its electric resistivity. The resulting change in the electric current is then measured by the readout circuit. For these detectors, it's important to have excellent thermal isolation of the phase change material to prevent any unwanted sources of temperature change. We want the detector temperature to change only because of the incoming IR signal and not because of any other heat channels like conduction. Although not always necessary, this approach sometimes requires additional temperature stabilization for calibration and improved sensitivity purposes. Because microbolometers do not need to be cooled, these IR cameras are referred to as uncooled IR cameras. These two approaches have developed over time for different purposes and needs. Cooled cameras tend to be faster and more sensitive, with a longer range of detection and better temperature resolution than uncooled cameras. However, cooled cameras can be more expensive due to the need for additional cooling and manufacturing challenges. On the other hand, uncooled cameras have advantages of being less expensive, smaller, requiring less power and maintenance, and having the ability to turn on instantly. The cooled cameras need time to cool down from room temperature before they can be used, which can take a few minutes. Infrared cameras have come a long way since the early 1900s when we started learning deeply about thermal radiation. At first, infrared cameras were developed for military purposes and were really bulky. But in the late 1900s, advances in nanofabrication helped to make them smaller and more affordable. The introduction of microbolometer uncooled detectors in the 90s was a major breakthrough as it eliminated the need for cryogenics and made IR cameras much cheaper. To give you an example of the cost reduction, there was a news article from 1997 that talked about firefighters using an IR camera that cost around $16,000. Nowadays, IR cameras are much more affordable and are being used for a wide range of applications. Here are a few examples of the use cases of IR cameras. Apart from the known defense and firefighting applications, the IR images give actionable insights for many different industries. They are now routinely used for inspection and equipment maintenance in residential and industrial buildings. IR camera is also used for medical diagnosis of selective diseases and animal health monitoring. More recently, thermal cameras are installed on drones are being used for thermography of large areas such as for solar farming maintenance and precision agriculture. The low-cost thermal IR cameras opened many new market segments. A recent market report by Yole Development shows different market segments in proportion to their value. Before the introduction of microbolometers, the IR cameras were costly and mainly used for defense, firefighting, and other limited number of applications. So, it was really the invention of uncooled IR cameras which lowered the costs and exploded the number of use cases within the last 20 years. We are currently living in a golden time of infrared cameras as its use is penetrating all sorts of professions and many new advances are expected for this technology. The scientists and engineers are working hard to further lower the cost of optics and improve semiconductor fabrication processes to lower production costs. With the latest computational advances, we can expect to see improved image processing algorithms in future IR cameras. In some cases, machine learning techniques are being introduced for robust fault monitoring for equipment maintenance applications. With respect to the IR photo detection itself, new fundamental modifications are constantly sought after. To give you few examples, in one study, the use of additional polarization filters in the imager helped reveal more details about the scene such as the buried landmines in the picture. From the perspective of materials science, the use of newly emerging 2D materials like graphene and carbon nanotubes can further advance the photo detection performance. Complex engineering of detectors to create a wavelength selective detector response has also been considered to provide more details about the scene. Because each object has a characteristic thermal emission spectrum, use of such multispectral or hyperspectral IR imaging helps to enhance contrast between different objects. It is important to note that such fundamentally new complex photodetectors may take a long time to reach the market because the production of such detectors at scale is a difficult manufacturing problem. In terms of new use cases, additional improvement in detection and sensitivity of IR cameras will be helpful for improving the remote sensing capability of satellites. Because Earth's atmosphere is transparent at some portions of IR wavelengths, the outgoing IR radiation can be detected, and the landscape can be imaged. This may help develop technology for real-time wildfire detection, which remains an unsolved, difficult and urgent problem. Some companies like See-Through are combining AR cameras with augmented reality headsets to help firefighters see through smoke. Imagine being able to see an IR image right in front of your eyes as you're walking through a building. It's really convenient and could be used for a lot of different things apart from firefighting, like equipment maintenance. It's exciting to see how IR technology is being explored in new and creative ways like this. That concludes my presentation on thermal IR cameras. I hope you found it useful. If you want to learn more, check out the links to references in the description. If you have any other technology topics you'd like to see me cover, let me know in the comments. Thanks for watching, and don't forget to like and subscribe to support the channel.